Our goal in this chapter and beyond will be to look at differential equations where the order is greater than one. In the previous chapters, we focused on the first order differential equation. Um, Here, we want to deal with differential equations of higher order, primarily the second order. That's basically where most of life is anyway. But the way it's introduced, it can be applied to third order, fourth order, and so on, whatever they are, right? Most of our equations, whether it's differential equations, ordinary or partial differential equations, typically you can spend a lifetime just in the second order, because that's basically where most of what we deal with in terms of temperature, gauging temperature, measuring temperature. How long will a substance, will it keep its form based on temperature over a period of time? So when do you have to adjust certain instruments? That's all second order, and that's in partial differential equations, heat equation, and various things like that. Whether it's differential equations or integration, it's either first, second order. And so here in this chapter, we want to be able to establish certain criteria to solving differential equations of higher order. What criteria? Well, we first examine what's called a homogeneous differential equation. And then secondly, a non-homogeneous differential equation. What do they mean? With that, we take the simplest form, which is a homogeneous differential equation. We take its form, we solve it. It's very easy to solve. It involves a lot of algebra, which hopefully for us, that should be a good thing. Well, I say that, and I have seen in the past where even in that, we've had some breakdown, and we've had some tears and some shedding of tears. But and people were amazed that in the past they really didn't know algebra. But the algebra is simple. Sometimes I think it's so simple that you kind of overlook it and think that it should be more than this, but it's not. And so people are thinking hard about something, but it's really easy. I tell my son at home when he's doing his work in high school that math has a way, if you allow it to work for you, it tends to work itself out. When I put my little bit in there, when I'm thinking, well, I think it ought to be, where are you getting that thought from? Is that thought based on any type of mathematical principle, or is it just you thinking or feeling? We get into trouble like that. So just let the math just, do what it wants to do. So we look at a homogeneous differential equation, and the simplest form of that is when the coefficients are said to be constant, like numbers. So you have derivatives, and then in front of those derivatives you have numbers like 1, 5, 6, 7. Easy to solve that, and I'll show you. But then we attach to that what's called a non-homogeneous differential equation. And we take the first part, you solve a homogeneous part of that, and then we'll solve the non-homogeneous part, which the non-homogeneous differential equation is a lot more involved. And so from this time on till the end of this class, we're going to look at methods of solving the same kind of problem, just in different ways, different variations. So in this chapter, we introduce what's called the superposition approach to solving a non-homogeneous differential equation, and then also variation of parameters, which is really neat because the application of it is universal. It's universal. I've taken some courses way out there, and the instructor in the graduate course at the University of Pittsburgh, he was solving some very complicated problem. And I mean complicated. It was really complicated too. It was complicated for him. So you can imagine how complicated it was for us. And he got stuck trying to solve this problem. And he said, he was thinking about using the computer program to write a code to solve it. And then he thought, oh no. He said, we can solve this by variation of parameters. Just old method from undergrad. So very good. We'll introduce that in this chapter as well. But we want to establish what's called the preliminary theorem. Boy, preliminary meaning it's the foundation by which, when you see that duck swimming on the pond or the lake, that duck is doing a lot of work up under the water. So it's a preliminary theorem that has all the work. You want to understand it. That preliminary theorem is called the superposition principle. And we'll talk about that in this section today. The superposition principle. It is the principle by which most of our mathematics, in terms of solving either a differential equation or what's called a linear algebra, is based on. There has to be some type of model that I have in my head in terms of why I'm solving this problem. What am I trying to get to? Grandmama, after a while, I never saw her using instructions, ingredients to cook certain things. She had it in her head because she knew the principle by which she was forming all these different pieces to her recipe, and she knew what it's supposed to look like at the end. So if I don't know what the problem or the solution is supposed to look like, then I'm just wasting time. I'm just doing stuff. So the superposition principle will tell us that when I get to the end result should look like this. Now, it doesn't say in particular what it should look like because we don't know what the particular answer should look like, but the framework for the answer has to match a certain way, the framework. Right? So to get there, we need to talk about some fundamental concepts of mathematics. One, linearly independent. Two, linearly dependent functions or sets. Typically in linear algebra, we talk about the same concept, but dealing with a set. Here, an example of a set would be a function or functions. So first, this definition for linearly independence and then linearly dependence. I want you to go on my definition in terms of learning this. My definition here, this information here is the book, but here, this is my definition for linearly independence. I say it's my definition, it's really a standard definition all over the world. Let's look at that. A set of functions, f sub 1 to f sub n, if we have here n functions, are said to be linearly independent on some open interval. The open interval is given some name, I, the same open interval from Calculus 1, by the way. If there exists, in Calculus 1, you dealt with things like the mean value theorem, Rolle's theorem, and so that's the same interval. That there exist constants, C1 to Cn, such that the linear combination of the functions with the constants is equal to 0. Here's the key. Implies that C1 equal to C2 equal to, and so on, equal to C sub n, they all equal to 0. That's said to be the definition for linearly independence. Let me back up and see what the author said. So he says that here, if there exists constants, he says not all 0, that's for linearly dependent, such that here the linear combination equal to 0. So his definition is not strong in that the implication is not stated in the right part. Here the implication is that the linear combination of the functions and the coefficients are equal to 0, but that's not it. The key to the definition is that this implies that this equation has to imply that all of my coefficients are equal to 0. That's for linearly independent. For linearly dependent, everything is the same, but the implication implies that not all the constants are 0. Not all the constants are 0. And I thought I had written out mine in here. I don't see it. I will put it in there. I will put that in there for you. I thought it was in there. It should have been right up under this definition for linearly independence. Yes, sir. No, individually, but they all will be 0. C1 is 0, C2 is 0. If you have 5 functions, then you're going to have, hopefully, the implications that 5, your constants, here, the C1, C2, C3, C4, C5 would be 0. Now, what does that mean, is the question. If a set of functions are linearly independent, it simply means this, that no function can be written as a linear combination or a scalar multiple of the other functions. If it's linearly independent, the function is said to exist on its own. It needs no help from any other function. So in other words, I can't take functions 1 and 2 and put some coefficients in front and say this is equal to function number 3. If they're linearly independent, they stand alone. I cannot write any type of combination of any other functions to give me another function. Linearly independent. Now, if you can do that, then you get the idea of linearly dependent. That means that a function does depend on other functions. That I can take functions 1 and 2 and I can write those as a combination to get function number 3. So function 3 depends on functions 1 and 2. But if I cannot do that, and that's what you're searching for in linear algebra, we said that if you have this linearly independent set or functions, and if they're set to span, that is that I can take 1 or 2 and I can produce other functions out there in the bigger space, then we say that these functions form what's called a basis. That's what we're building here. But we don't have to say basis here for differential equations. We call it a fundamental set. And a fundamental set says that if I have functions that are linearly independent, that's very strong. That means that these functions are not, if I can use the word weak, they're not weak in that. A weak function would be, in my own southern Alabama, terminology, a weak function would be a function that needs another function to exist. But a strong function, he stands all alone by himself. He don't need anybody else to help him, And when I go to a church meeting and I raise something at church, I look around and I see folk, I tell them, look, go ahead and speak your mind and you vote. And then they looking at so-and-so, what you gonna say? What you looking at him for? You need that person to help you think. You got to be able to speak for yourself. Then when that leader over here, when they say something, then 2 or 3, they say, yeah, we agree with brother so-and-so. That's a dependent set. That's a dependent set. We want linearly independent, that you make up this decision on your own, based on your own experience, or did somebody just tell you? That's linearly dependent. Then we look at mathematically how we can show that functions are either linearly independent or linearly dependent. On the test, you will have to write out this definition. You would have to write out on the test. I would say define linearly independence. I'm looking for this definition. To write it out in detail. From the beginning to the end.
Will we have to write out the linear dependence?
Yes. And I will go back and add that into my notes. I thought it was here, but it's not. But I will state it exactly the way I think you ought to know it, and then you can, to rephrase it, rewrite it thereafter. But you need to know what it means for a set of functions to be linearly independent. And we'll look at some examples to show what this means mathematically. Functions are linearly independent if you can write one function as a linear combination, that is or in other words, a scalar multiple of others. We'll look at some very neat examples of that. We take two functions, f sub 1 and f sub 2, and to examine the nature if they are said to be linearly independent or linearly dependent. Function 1 is f equal to x, f sub 1 equal to x. Function 2 is f sub 2 is equal to the absolute value of x. Now the question is, can I take one function, take function 1, and can I write it as some type of scalar multiple to produce this function number 2? And here, let's see if I can pull this. I'm missing some of my page. Well, I guess that's all that we can see. Functions 1 and 2 here are said to be linearly independent. Functions that are linearly independent cannot be written, this is important, as scalar multiples of other functions. Let me show you. Here's this example. The set of functions f sub 1 equals to cosine square x, f sub 2 equal to sine square x, f sub 3 secant square x, f sub 4 tangent square x. Here they're said to be linearly dependent on the interval, this interval here, because if I take the linear combination of all these functions coupled with some coefficient in front, c sub 1 times cosine square plus c sub 2 times sine square plus c sub 3 times secant square plus c sub 4 times tangent square equal to 0. If it's equal to 0, can you find scalars c1, c2, c3, c4? If all c1, c2, c3, c4, if they're all 0, then these functions are said to be linearly independent. But if you can find scalars such that c1, c2, c3, c4 are numbers such that the combination of these guys equal to 0, but these constants are not all 0, then the functions are said to be linearly dependent. Well, here what they did was they went ahead and found those scalars. c1 and c2 is 1, so basically you get cosine square plus sine square is equal to 1. And then here, c sub 3 is negative 1, and then c sub 4 is 1 because tangent square minus secant square is equal to 1. And so then you get, that'll be negative 1. So then you get 1 plus a negative 1 gives you 0. But not all the constants are 0. See that? C1, C2, they're numbers. C3, C4, they're numbers. So since they're numbers and they're not 0, these functions, sine square, cosine square, secant square, tangent square, are said to be linearly dependent. Set of functions, f sub 1 to f sub n, is linearly independent on the interval if at least one function can be expressed as a linear combination of the remaining functions. Here's an example. Take this function, f sub 1 is the square root of x plus 5, f sub 2 is the square root of x plus 5x, f sub 3 x minus 1, x sub 4 is x squared. Here they say it says linearly dependent on the interval from 0 to infinity because f sub 2 can be written as a linear combination of the other three functions. Here, observe. F sub 2, which is the square root of x plus 5x, can be written as a 1 times the first function plus a 5 times the third function, and then 0 times the fourth function. And here that will produce for us f sub 2. If that happens, if either you can write one function as a scalar multiple of the others, then the functions are linearly dependent. Or when you list the functions out as a linear combination and you get 0, does that imply that not all the constants are 0? Linearly dependent. Now, we got a problem or so in the homework that would answer that. We'll come to that in just a moment. Homogeneous differential equations. The nth order linear differential equation here is homogeneous, and what makes it homogeneous is that equation number 6 is set to equal to 0. That's all. That's all. If there's a differential equation set to equal to 0, it's called homogeneous, period. This term homogeneous is not to be confused back in chapter 2, where we looked at what was called a homogeneous equation. It was different, same word, but they're talking about two different things. So you want to be careful there. Back then, we said that a homogeneous equation was an equation whereby, you remember that the powers had to match up. If it was like x times y, then you can have x squared, you can have y squared. And we said that it's homogeneous, if they're all, second power, if they're all first power, even with the combination like x times y, looked that to be like a second power. We call that homogeneous. We're not talking about that type of homogeneity here. The homogeneity there is interesting. That term homogeneity comes by what we call a Banach space. Have you ever heard of a Banach space before? Or a Hilbert space? These are higher spaces, and either as finite dimensional or infinite dimensional vector spaces. We're talking about certain spaces out there that exist, Banach space or Hilbert space. In defining, or even an inner product space, linear algebra, we try to hone in on the so-called inner product space. Everything after that builds on the inner product space, whether it's a metric space, Banach space, or Hilbert space. There are other spaces out there as well. But in the definition of the Banach space, one classification is that the function or that the vectors are said to be homogeneous. And that's back in chapter 2. We talked about the homogeneous equation. That's where it comes from. That's where it comes from. In other words, that if I take a scalar, and if I run the scalar through the function, or if I run the scalar through a set or through a vector, can I pull that scalar out and look at it as the absolute value, and does the function still maintain its order? That's said to be homogeneous. Here, we're not talking about that type of homogeneous. Here, we're just simply saying a differential equation set to equal 0 said to be homogeneous. If it's not 0, like equation number 6, if there's not 0 there, but there's a function like equation number 7, and this function g of x is not the 0 function, we call it simply non-homogeneous differential equation. We will solve, our goal in this chapter will be to solve equation number 6 and also to solve equation number 7. Doesn't matter about how high the order is, we'll still solve it. Your quest here will be, if you're given functions, can you determine that these functions are linearly dependent or linearly independent? Well, there's a few ways that we can do that. One quick, straightforward method is called the Warren scheme. The Warren scheme. I want to determine whether or not the functions are linearly independent or linearly dependent. We take what's called the Warren scheme. Here the Warren scheme says this: if you give me n functions, f1 to f sub n, then we want to make sure that each function I can find at most its n minus 1 derivative. So if I got 5 functions, then all you need is the 4th derivative of each function. So here possesses at least n minus 1 derivatives. So we said that the determinant here of these functions, this determinant, basically I take each column, the head position of the column is the function, and below it would be its derivative. So if I got 3 functions, then below each function is going to be the first derivative, the second derivative. So if it's n, I look at n minus 1 derivatives. Right? So if I have 4 functions, then I list the functions in that first row, and then if there's 4 functions, it'll be the second row is the first derivative, the third row is the third row is the second derivative, and then okay, you know what I'm talking about. If it's 4 functions, I only need 3 derivatives, first, second, and third derivative. Now, the criterion here with the Warren scheme says, and the definition of the Warren scheme says, this is it. Just find the so-called determinant of these functions. But the theory of Warren scheme says that if the determinant is not equal to 0, then the functions are said to be linearly independent. It's called here the criterion. It's the theorem associated with the Warren scheme. So here, if you have these functions, here they up in the definition they call them f sub 1 to f sub n, but here in this theorem they call them y sub 1 to y sub n, the same thing. So the set of solutions is linearly independent on this open interval I, if and only if the Warren scheme is not equal to 0. So if the Warren scheme is not 0, then we have linearly independent for the functions. Well, the contrapositive is true. That is, that if the Warren scheme is equal to 0, the functions are linearly dependent. Right? Stands to reason. Right? If the Warren scheme is equal to 0, the functions are linearly dependent. If the functions for the Warren scheme, if the Warren scheme is not equal to 0, the function is said to be linearly independent. If the functions are linearly independent, then we call those functions a fundamental set. It's a very strong case that wants to help us build what's called the superposition principle. So if the functions are linearly independent, then those functions are said to be the so-called fundamental set. Let's talk about the superposition principle, then we'll work some problems here. The superposition principle tells us the framework of how we are to write the solution, basically to every problem in chapter 4 and beyond, how we're going to write the solution. Superposition principle says that the solution is going to consist of 2 parts. It's going to consist of the solution for what's called the homogeneous equation, but then it will also consist of the solution for the non-homogeneous differential equation. So here, that's why they say the superposition principle for homogeneous equations. Well then, it stands to reason that there has to be a superposition principle for the non-homogeneous differential equation. The superposition principle for the non-homogeneous differential equation includes the principle for the homogeneous part, because the homogeneous part is included in the non-homogeneous. So if I have a differential equation, let's go back to equation number 7. See how he references differential equation 6 And then for the non-homogeneous, he'll reference the differential equation that was number 7. I think it was here. It's the next page. He's referencing this equation number 6. It's a homogeneous differential equation. So he's saying here's a solution based on the superposition principle for equation number 6. Then when we talk about the solution for the non-homogeneous differential equation, he's referencing equation number 7. Now notice, look at equation 6 and 7. The only difference is one is equal to 0 and the other is equal to some g of x. So obviously, whatever you use to solve the part on the left for equation 6, it's the same thing that you use to solve the left side for equation number 7. So the solution for equation number 7 includes the solution for equation number 6 plus something else because you got that g of x over there. So what he does is he takes the solutions, like the solution for number 7, he says the solution for number 7 is the solution for equation number 6 plus the particular solution for each g of x. Let's see. So here, theorem 4.1.2 says that let y sub 1 to y sub k be solutions of the homogeneous nth order differential equation. Basically, what they're saying is that the solution that you found when you solve for equation number 6, those guys are going to be linearly independent. Those functions will form what's called the fundamental set. So if that be the case, then we say that the general solution here for the homogeneous differential equation is said to be y equal to each of those solutions that you found here coupled with a constant c1 times y sub 1 plus c sub 2 times y sub 2 plus and so on. So the general solution for equation number 6 is said to be a linear combination of those that fundamental set y sub 1 to y sub k. It's good stuff. Theorem 4.1.5 is just a copy of that previous theorem. And the only difference is that he's saying what these functions are, y sub 1 to y sub k, and they are the fundamental set. Basically, they're linearly independent. So he could have saved some time and just said one of them, and that would have been sufficient. Now, we call the general solution for the homogeneous differential equation, we call that the complementary solution. So I'm going to have, for the homogeneous differential equation, I call its solution the complementary solution. And then for the general solution for the non-homogeneous differential equation, I call its solution the linear combination of the complementary solution plus a particular solution, y sub p. It's a particular solution. Who had linear algebra? Do you remember in linear algebra how we dealt with it? Was the same principle. It was the superposition principle. As a matter of fact, in linear algebra, this is where the principle comes from. Differential equations is a subset of linear algebra. So now I want to be able to solve equation number 7. So what I do is I solve its homogeneous part first. Set the equation equal to 0. I solve that. That gives me the so-called complementary solution. You know, this c sub 1 times y sub 1 and so on to c sub n times y sub n. And then I do more work, and then I solve that non-homogeneous part where that differential equation is equal to some function g of x. It's a little bit more intense to solve that. But whatever that solution is, I add it to the complementary part, and I get a general solution. Right. Now, what we're going to do in this section is we're not going to solve. They've already solved the problem. They asked us to verify the solution. That's all we got to do, is to be able to show that this is indeed the solution. Now, folks, I tell you what. Now, back 10 years ago, I would get up on this desk, but I tell you, man, time brings about a change. You know, you got to make a dramatic statement to get people's attention. You know, when our Lord, when he went into Jerusalem, he rode a donkey. He didn't have to ride a donkey, but he had to get their attention. He was dramatic, right? Yeah. When he was on the cross, the Bible said that he cried with a loud voice. Said it's finished. He didn't have to cry with a loud voice, but he was dramatic. So I can't get up on the desk today, though. But you understand what I'm trying to say? Is this is important? Well, I lost my thought of what I was going to say. So anyway, talking all that stuff. Anyway, okay. The solution, the general solution. Let me pull this up. The general solution to the differential equation for equation number 7 is said to be its complementary part plus its particular part. All together summed up gives us the general solution. Now, y sub c is the general solution for the homogeneous differential equation. Y sub p is only a particular solution for each g of x. Now, the theorem that comes after this, I didn't even put it in here. It actually gives the general solution, which is basically y sub c plus the summation of all of these particular solutions. So it would be the summation of y sub p sub I as I goes from 1 to whatever n, or how many solutions that there may be for the particular solution. So what we're going to do, oh yeah, here's what I was going to tell you. The problem here that I give you on the test is easy, because basically it's going to be a similar problem from this section where they give you the answer. They just ask you to verify, is this indeed the answer? So they give you the answer, just take the answer and you plug it into the problem and just show that the left side equal to the right side. I've had people who, they wouldn't even do that, and it was 10 free points. So let me show you. We give you the solution and just say, just verify. It's like almost like saying, this is an algebra problem. Here's the answer. Just plug it back in to make sure that this is indeed the answer to this particular problem. That's all you got to do. Let's see. Now that problem would be here, numbers 23 to 30, and I get to that where you just have to verify. They give the solutions, just verify if these guys are indeed the solutions to this particular differential equation. But let's start with showing whether or not functions are linearly independent or dependent based on what I started off with the lecture. If you're given some functions, can we show that they are linearly independent or if they're dependent? Sometimes you can use the Warren scheme. Sometimes you can look at them and be able to kind of piece together if they're going to be linearly dependent. Let me show you what I'm talking about. So let's take this problem here. We have here 3 functions. We want to determine whether or not they are linearly independent or linearly dependent. Sometimes you can use the Warren scheme. If the functions are complicated, the Warren scheme, because you have to take like the first derivative, second derivative, sometimes third derivative, that could be a whole lot, depends on how these functions are written. So if you see that that's going to be too complicated, then you might be able to look at those functions and see if you can piece together whether or not they're going to be linearly dependent. What I'm going to do is just use the Warren scheme for this guy, because these functions don't look to be that cumbersome. So I have the Warren scheme of the functions x squared, and 4x minus 3x squared is equal to the determinant. Here, the first function is x, its derivative is 1, its derivative is 0. The second function, x squared, its derivative is 2x, its derivative is 2. and then this last function, 4x minus 3x squared, its derivative is 4 minus 6x, and then its derivative is negative 6. Now, remember that this is a determinant. If you hadn't had linear algebra, I think in physics, you all found the determinant by taking the first two columns and just rewriting them over on the right side. So you take x1, 0, write it over here to the right, and then x squared, 2x, and 2, write it over there. You're welcome to do that. That's fine. I'm going to use cofactor expansion. Cofactor expansion, and I'm going to try to use it in a very easy way so that I can get the answer real quick. I can use matrix reduction to reduce this matrix so I can get the solution for the determinant very quickly. And what I mean by that is, you know, in row reduction, you can use an entry to cancel out entries below it or above it. You know, like you can take the x and you want to get a 0 here where that 1 is. I'm going to take this 1 and get a 0 where that x is by basically saying x times row number 2, add that to row number, well, subtract. So it'll be negative x times row number 2 plus row number 1. So basically I'm going to have negative x plus x to give me a 0. But everything else would change, you know, for row number 1. So let me write my operation. So here, I'm saying negative x times that row number 2. And I'm going to add that to row 1. So I'm going to go ahead and rewrite rows 2 and 3 because they don't change. My change is on row 1, so negative x times this one is negative x plus x, gives me 0. Negative x times 2x is negative 2x squared plus x squared is just negative x squared. And then negative x times this 4 minus x 6x will be negative 4x plus 6x squared. So I'm going to put this in red. So this is negative x times 4 minus 6x plus 4x minus 3x squared. So this gives me negative 4x plus 6x squared plus 4x minus 3x squared. So they cancel out and I have left a 6x squared minus 3x squared, which is just 3x squared. Now I did that because I know in linear, and I'm saying linear algebra, but when I was in the 11th grade, we did matrices. So I went to a very poor school, so they didn't teach calculus in high school, but they made sure that we knew everything else. So when I got to college, calculus was easy. Well, not the first semester. It took me a while to get used to calculus. But I had a very good instructor who believed in grace, and I believe in grace too. So the reason why I canceled this x and got a 0 there, because cofactor expansion says that I can expand along a row or I can expand along a column. And so if I expand along a column, then all I'm doing, this is 0 times a subdeterminant, which that cancels out 0 times whatever is 0. I get to this 1, I'm going to cancel out its row and its column, so it's the subdeterminant of this negative x squared, negative 6, 2, and 3x squared. And then plus this 0 times its subdeterminant, that stuff cancels out. So here's what this is. So I'm going to expand along the this first column. So I'm doing cofactor expansion along the first column. So here, this one scheme, here, these functions of x is equal to, it's 0 times this, I'm not going to even write it. I mean, I can. This is 0 times this subdeterminant. I get rid of its row and column, so it's 2x, 2, 4 minus 6x. It doesn't matter because it's 0 times that. It's going to be all 0. And then it's plus, let's be negative. Minus this 1 times its subdeterminant. I get rid of its row and column. So this is negative x squared, 3x squared, 2, and negative 6. That is, wherever this 1 is, I cancel out this row, I cancel out this column, then there's these 4 terms that's left. And then plus this last 0 here, which I get rid of its row and column, so it becomes what's left, these 4 entries here. Just negative x squared, 3x squared, 2x, 4 minus 6x. Well, the goal is for cofactor expansion, what makes it easier for you is that if you have a row, if it's three entries, if you have 2 of those entries is 0, then basically you're just doing the determinant on that entry where you don't have a 0. So it could be a row or it could be a column. In this case, it's a column where I have a 0 here and a 0 there. So my determinant is based on this 1, deleting its row and column. What's left would be this negative x squared, that 2, 3x squared, and that minus 6. And the permutations from linear algebra, the permutations were, plus sign here, minus sign there, plus sign there, minus sign here. That's why it's a minus here. Plus sign there, minus sign here, plus sign there, minus sign here, in front of that subdeterminant, and then plus sign. So here I'm expanding along this first column. So it's plus 0, right, minus 1, and then plus 0 there. Right. But again, this is just my method, cofactor expansion. Again, you have done this using the method from physics where you just rewrite the first column and the second column, and then you do, it's called the arrow technique. You use that, that's fine. You get the same result. And I could have done my method right here and just really did it in 5 seconds. I'm just trying to explain what I'm doing, but it's really quick. So here everything is based off of this guy, because this is 0, because of that 0 in front multiplied. That's 0. And so here the Warren scheme is based on this guy. So this is the negative in front. This is positive 6x squared minus, it becomes this times that, then minus this term times this term. So it's 6x squared, right? Then minus 2 times 3x squared, which is 6x squared, is 0. So these functions are linearly dependent. If the Warren scheme is equal to 0, then the functions are linearly dependent. That's all. Now, however you get that is fine, because I could have came here, and let me go back and do something else, and I'll show you. Linearly dependent. I could have done this, and I would It would have been fine if you had done that. I could have said that negative 4 times f sub 1 plus 3 times f sub 2 plus f sub 3 is equal to 0. You agree with that? Negative 4 times f sub 1 plus 3 times f sub 2 plus f sub 3 equals to 0. Let's see. Negative 4 times f sub 1, that's x, plus 3 times f sub 2. F sub 2 is what, x squared? Then this is plus f sub 3, which is 4x minus 3x squared. Isn't that 0? But notice here, not all the scalars are 0, right? Because c sub 1 is equal to negative 4, c sub 2 is equal to 3, and c sub 3 is equal to 1. Right? There's a 1 times f sub 3. We said that for functions to be linearly dependent, it means that the linear combination of the functions with constants is equal to 0 implies that not all the scalars are 0, thus linearly dependent. Whether you use the Warren scheme or you just look at it and piece that together, where c sub 1 times f sub 1 plus c sub 2 times f sub 2 plus c sub 3 times f sub 3 is equal to 0, but c sub 1 is not 0. C sub 2 might not be 0. You just need one of them not to be 0 to get linearly dependent. You get linearly independence if the linear combination of the functions with the constants equal to 0 implies that all your scalars are 0. The functions stand alone. See how with this function, with these functions, you can write functions 1 and functions 2 as a combination of function number 3. I can take function number 3 and say function number 3 can produce functions 1 and functions 2. Or functions 1 and functions 2 together can produce function number 3. That's dependent, right? That's dependent. Functions depend on another function. But if it's linearly independent, they don't depend on each other. Okay? The combination of the scalars and those functions would imply that the scalars are all 0. I'll show you. Those were C1, C2, and C3. They came from looking at function number 3. Let me go back up and look at this. So here's function number 3, right? Here's function 1, here's function 2. Look at function 1. This x is similar to this 4x, but I need a 4 in front. Matter of fact, a negative 4 to get negative 4x plus 4x to give me 0, right? And then for f sub 2, to cancel out this negative 3x squared, if I put a positive 3 in front of that x squared, then I get 3x squared minus 3x squared gives me 0, right? Yes, sir.
So give me the opportunity to do that with something like that simple, if instead of that rather than
Yes, like number 17. Okay, that's a good question, JC. Thank you. That's a good transitional question. We learned that in English. The only thing I learned in English. Because when they said transition, I was thinking two things. I was thinking, okay, in algebra, you know, we have transitional statements. That is basically, I do this line, I do this next line, I simplify, I do the third line. That was a transition. And then when I read the Bible, I found out there was another transition. But anyway. Yeah, okay. Do you see how we can take number 17? Number 17, these guys are linearly dependent. What should the constants be to formulate linearly dependence? Okay. Should be a negative somewhere because you want to get 0. Well, either the negative is going to be on f sub 1 or the negative will be paired with f sub 2 and f sub 3. So here, c sub 1 times f sub 1 plus, and there should be a question here, c sub 2 times f sub 2 plus c sub 3 times f sub 3 equal to 0. Question. All right. Well, if so, what can C1, C2, and C3 be to yield linearly dependence? So I would say let C sub 1 equal negative 1. C sub 2 would be 5. C sub 3 would be 5. And there's several combinations that you can use. Several combinations. So let's see if that works. So this is negative 1 times the 5 plus 5 times cosine squared x plus 5 times sine squared x. That does give me 0. Well, let's see, this is negative 5 plus 5 times cosine squared x plus sine squared x, right? Well, this is negative 5 plus 5. But here, notice that c sub 1 is negative 1, it's not 0. C sub 2 is 5, and C sub 3 is 5. Not all 0. That implies linearly dependent. Yes, sir. For linearly independence? For linearly independence, you want to be able to show that there's no other scalars out there. If you got this equation equal to 0, there's no other choice for the scalars but each one to equal to 0. C1 equal to 0, C2 has to equal to 0. I mean, it has to be. There's no other choice. If it's possible where there are other choices, then you're talking about linearly dependent, right? And it just begs, the rationale for that question of linearly independence, linearly dependence, excuse me. Now look at this one. Now here, I will use the Warren scheme. What's this determinant? For the determinant, if you have a row of all zeros, the determinant is equal to 0. If you have a column of all zeros, the determinant is automatically equal to 0. 0. Either one. If it's a column of all zeros, determinant automatically is equal to 0. If you have a row of all zeros, don't do any work. The determinant is equal to 0. You're done. Okay. Yes, sir. There's a few rules there involved with it. I mean, you can look it up online. It's very straightforward. Yeah. But either way, how you want to find it. Like I said, let me show you this. Here, look at this Warren scheme. This is x, 1, 0. This is x minus 1, 1, 0. This is x plus 3, 1, 0. I give you another problem. But here again, this whole row is 0, all zeros, so the determinant is equal to 0. So we get linearly dependent. Let me give you this example. So if we have the first function, let's say is equal to 6x, f sub 2 is equal to x squared, f sub 3 is equal to e to the 5x. So you're looking for the Warren scheme for these functions. So this is 6x, 6, 0. This is x squared, 2x, and 2. This is e to the 5x, 5e to the 5x, 25e to the 5x. If you wanted to come here and list that first column and then the second column, didn't you do this in physics? There, where you multiply these terms together, multiply those terms together, multiply those terms together, right? Does that sound familiar? So here, that would be the 12x squared times that 25 e to the 5x, and then this is plus 0 plus here 12 times e to the 5x. And then when you go in the opposite direction, you do a minus in front. Right? So you multiply those terms, multiply those terms, multiply those terms. So this is now minus 0, then minus here 60x times e to the 5x, and then this is minus here, that 6x squared times the 25 as e to the 5x. And then you simplify that. The way you get these numbers here is the same way for cofactor expansion. So my statement before was, whichever way you prefer to find that determinant is fine with me. You can use, this was the arrow technique in physics, you can use that, or you can use cofactor expansion. If you know about cofactor expansion, use it. If you don't, whichever method you know, I'm fine with that.
Our teacher said he didn't like this method, so
I don't like it either.
we used some kind of, we almost did a, remember? We didn't like this method, so he made us something he broke our boxes or whatever. Yeah.
Did he use cofactor expansion? Okay, yeah. Cofactor expansion is the standard, the standard method. Let's see, let me stop there and then I'll finish this section and cover 4.2 on Wednesday. Thank you.